I'm muted. I got coffee, but I was muted there. How's everyone doing? We got coffee. It's time to start some office hours. Who's here and who has questions? Let's get started with some office hours. What questions are there? What do you want to talk about? We got the project. We got some assignments. We got Canvas content. What are we talking about today? Can you up on the two cross question? The standard deviation is the estimate of the standard error of a sampling distribution. Did they call it that? I'm about to, let me see. I've got all the, let's see. That's so weird. Let me close that out. My YouTube has been acting up pretty weird. Let me go find this. Great question right there about that. Let me find that one. I'm going to find that specific question. I feel like it's a true false. So I want to take a look at this one. Chapter 14. Let's see. Okay, I've got them all open right now. And this is on the Canvas content tonight. Oops, gotta find it. Okay, here we go. The standard deviation is the estimate of the standard error of a sampling distribution. They're gonna say true to that, aren't they? Saying false. Yeah, I don't like this question. And I'll tell you why. Because, and I'll explain. Good to see you here, Dean. Awesome. Thank you so much, Dean. I appreciate that. Thank you so much for the positivity right there. So I'll explain. I feel like I need to work on my green screen on it. Well, it says the answer is false right here. It shows the answer is false. And I'll explain why. Let's go to the notes and explain why this is false. And I'll explain just why I don't like it. It's such a weird question. So the reason is false. It can be done anytime during, but I'd like to see you to create some of the graphs. Yeah, of course. Let's do some graphs on project, all that good stuff right here. So here's why it's false. Let's go take a look at this. Okay. So when we use the standard error is created when you know S. So here's why it's false. The standard error is created when you know S. We don't use the standard error when you know sigma. So this right here is not the standard error. This would be the standard deviation of the distribution. So it's a blending of topics and saying something that is true for another portion. And we deleted the notes portion today. Well, here it is, standard deviation. So this is the standard deviation right here, where this is sigma over square root of n. And that's what I was worried. I was like, they're going to say. So that's where, I got it wrong when I said true. Yeah, it's false. Because this is the standard deviation. It's not a standard error, it's a standard deviation. I'm only going to write a note to Terry. Know what I'm going to do for us? I've got it up still. If you got that one wrong, just tell me. I'm going to remove it for now. Let me go here. Standard deviation is just, I just don't like this question. So it's gone. I don't think that's a good question. Yeah, I just think it's such a small. Let me read this other one. All other things being equal, the larger the sample size, the smaller the standard deviation. Yeah, it's pretty obvious right there. That one's good. It's just using two concepts and blurring them together, because this is the standard deviation for the distribution of the sample mean, and then down here we see in other equations the standard error for the confidence interval when creating a sample mean, or to estimate the true mean. So here's the standard error that's used when we create confidence intervals. And here's the standard deviation, which is used when we know the truth. So it's basically saying it's a false statement. It should be like a better way of wording that would be, when we create confidence intervals for the true mean, we use the standard error. That'd be a true statement. So looking at the equations, when we create confidence intervals for the true mean, we use the standard error. That's a true statement. Does everyone have that? Write that down right here. When we create confidence intervals for the true mean, we use the standard error. So that's the standard error right there. When the three conditions for the sampling portion must be met, calculate the sample average. So do we need to meet the conditions to calculate the sample average? Do we need to meet the conditions to calculate a sample mean? So do we need to meet the conditions to calculate the sample mean? To calculate the sample mean, So we have here, would we need to know the three conditions are met to find the sample mean? And why do we need to meet the three conditions? Why do we meet the three conditions? Is it to calculate? Yep. There we go. Layla's right there. We meet the three conditions to calculate or to show that it's approximately normal. So that's the whole goal of the central limit theorem. It's not to calculate the sample mean. It's to show that the distribution is approximately normal. So by meeting the three conditions, we can show that it's approximately normal. We don't need to meet the three conditions to show that it is to calculate the sample mean. Let's do one version of the quiz right here. Let's get that quiz up. Let's go to the quiz. Let's do a version of the quiz. Where is Alt? Go here to the home screen. And go down here to Canvas content number 8. I think we're going to do some graphs here in a little bit. Thank you, Sam. We'll do some graphs. And here's the quiz. Okay. Let's take a look. Oh, you can't see it. There we go. And let's take a look at the Canvas content quiz. Here we go. An employee of the Guinness Brewery Company invented the tea distribution. True or false? Oh, you should know this today if you were in class. You should be like, I'm okay with this question. I mean, it's a fun factoid. I mean, it's either true or false. It might be also time traveling Mr. T invented it. But is that true or false? We do some Canvas content 9 here in a little bit. We can do it towards the end. You got it. We'll do some graphics, and then we'll do this. And then I think Ritu will do Canvas content 9 here a little bit. That sounds good to me. We'll do that after we do, I think we have graphs next. And Guten Tag. Like, is that German up there? So is this true or false? An employee of the Guinness Brewing Company invented the tea distribution. Is that true or false? An employee of the Guinness Brewing Company invented the tea distribution. Is that true or false? Very true. That's William Sealy Gossett. And he didn't want to name it the tea distribution because who was it? Wasn't Hunter? Fisher. Fisher wouldn't let his work go through. So Ronald Fisher didn't like the work of Gossett, probably because he was like some beer guy, and they wouldn't let his work go through. So he published it under the pseudonym Student. So it's a very true statement. Which of the following is not a requirement for testing means? So what is not a requirement for testing means? Let's go look at our conditions. I'm going to pull up the conditions right here. So what is not a requirement for testing means? 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 What is not a requirement for testing means right here? What is not a requirement for testing means? I know, Ben. I'm sorry. I hope it looks okay. So I cut my hair. I did it. We got more videos to come. We've got don't worry, we had a fun video today. Here, wait, watch this. I gotta do this though. Hey everyone, welcome to Stat to One. How are you doing this morning right here? How's everyone doing? Everyone doing all right? I think I got something in my hair. Just one second, real quick here, everyone. Oh man. Just like instant haircut. Oh, look at that. Just so quick, so cool. There we go. Head back over to the main screen. Oh, it's going to play again when I go back to the main screen. We'll just make sure to stop it. So, what do we have right here? What I think people, success, failure, great job, Layla. We're having a little bit of fun right here. Success, failure is for categorical data, so that's not there. The three conditions for, thank you, Ben. The three conditions for the sampling distribution must be met in order to calculate the sample average. No, you can just calculate the sample average at any point. All things else being equal, the larger the sample size, the smaller the standard deviation of the sampling distribution. And we were doing a lot of these problems today. So all else being equal, the smaller the standard deviation. So what, is that true? All else being equal, wait, the smaller? Oh, look at that. All else being equal, the larger, okay, good, larger the sample size. All else being equal, the larger the sample size, the smaller the standard deviation. Is that a true statement? All else being equal. What do you notice here about this equation? There we go. You can see the equation now. There's the equation. So it's S over square root of n. So all else being equal, the smaller the standard deviation, the larger the sample size, the smaller standard deviation. So if you look at this equation right here, very, very true. Great job, Cad, right there. If you look at this equation right here, this is sigma over square root of n right there. So if we make a larger sample size, all else being equal, we're going to see a smaller standard deviation. So that's literally talking about this equation right here. This is a very, very true statement. No matter what the shape of the parent population is, as long as our sample size is 10 or greater, then we will have an approximately normal distribution. If our distribution is very what, this will not be met. And we went over this today right here. If our distribution is very what, and here's our slide. So all else being met, as long as we have 10, we're good. All else met, if all else being said, if we have 10 observations in our sample, our distribution of our sample mean will be normal. That's not how the large enough n condition works. What do you think? What do you think? If we have 10, it better be closer to normal. So if we have 10 observations, it better be closer to normal. So this would not be met right here. This is not true. So this is a very, very, very false statement right here. So this is a false statement. We should have it. And there we go. 10 out of 10. Good stuff right there. Any last questions about the Canvas content? I think a lot of people are getting 10 out of 10s on these. Make sure to write down the questions, practice them, review them. More than memorize them. Think about how... I know, Adam, I'm so sorry. You should rewind. I played my secret video this morning. I'm sorry. It'll return. I'll just grow it out again. I'm short hair Brian once again. Then I'll go to medium length hair Brian, and we'll just keep going down and down and down. It's so good to see you, Adam. Thank you for swinging by. Seeing a squint now, you see my crow's feet more. No! My long hair was hiding my crow's feet. No! So... let's see. We're going to do some... like Adam's like, the flow is gone. No. Let's continue on right here. Let's look at some data. We got so many graphics. Look, we were looking at this data last time. Okay, so we're going to do one graphic from each of these. So you can do the first graphic in... Here, we'll put a cut in the video. Hey, everyone. Welcome to Stats. Oh, that Brian's gone. Look at the color. There's so much lighting color change. Like, that's the nighttime... I look taller without there. There you go. Anyways. So we're going to do some project right now. Let's do some project here. Let's hop over to the project. Let's do this. Okay, so let's work on the project. I'm going to touch this hair just as much as the old hair. So let's start working on the project right here, and let's talk about some decision trees. What kind of data can a decision tree take? Can anyone tell me what kind of data a decision tree can take? I'll pause right there while I make this decision tree. What kind of data can a decision tree make? Any thoughts on what kind of data a decision tree can take? That's how we go to make a decision tree. Let's go for the project. Can I use the same data as I did a little bit of executive summary? Yeah, that's fine. Yeah, if you aced the executive summary before, you could do that. Just kind of change up, maybe like, just keep it similar. I have some videos. I'll put them in a playlist, Carly. So we'll go over that here right now. And then unless people are like, make the playlist now, I can make the playlist now. I just forgot over the weekend to make the playlist and send it out. But I'll make the playlist and I'll send it out. So I will send out a full playlist. I went and got some food between breaks. I didn't have time to do it. And I was like, oops, sorry about that. So decision trees can take categorical and quantitative data. Now, what you don't want to take identifiers. You will lose points. I'll probably take off points some. I think I have it on there. I'll probably take it off on the making of the decision tree if you put in identifiers. So it's just an error in doing it. Maybe I should update the rubric to say you'll lose points if you add an identifier. I think I said that in the instructions. And then the rubric should also say that. I don't want to update the rubric a lot, but you just do not want to include identifiers in there. So that would be an error in creating your tree. So we're going to go ahead here and take all the variables and you put them all here. And then you choose what variable you want to create. I clicked the top variable. For those who saw what I did, I clicked the top variable. I scrolled down, I hold shift, I click the bottom variable, and that selects everything. So that's just a quick way of selecting everything but the student number. You could also click Control A or Command A, then hold Control and deselect something. That's another way of doing it. So now we're going to take a y variable of interest. It can be any of these. Like, let's say we want to explain how attractive people think they are. Why do people think they're attractive? And so you'll notice this tree is quantitative, not categorical, but I want to explain who thinks they're the most attractive. Oh, wait, so do we have a variable here? Oh, their own attractive. I'm going to remove out that variable because that's kind of boring. Like, people rate their own attractiveness higher when they think they're more attractive than other people. You know what? Let's not do most attractive then. Let's do, why do people think they're smart? Ooh, there we go. How'd you get to the decision tree? To get the decision tree platform, go to Analyze, Predictive Modeling, Partition right there. Here, I'll make it bigger so you can see. Well, you won't use them all. You should try to put all of them in there. I'm going to zoom in so you can see on this. There we go. That should be on the screen. No, is it right off? You should put all of them in there, and it'll go through and find the ones it wants for you. I think you can see that. So it'll find the variables it's going to decide to use. So it'll pick the variables that it's going to use. Like, you won't tell it which variables to use. You're welcome, cat, anytime. Oh, wrong button. Don't leave class yet. It'll pick the variables for you. So when you go here, we're going to select everything, and then we're going to put this over here. And remember we hit here, and then we hold shift and click the bottom. And then we want to maybe predict something like, why do people think they're intelligent? You can pick whatever you want. Just make sure you drag one variable up here to the top and then click OK. So you should have one variable and a bunch of X's. You're probably all right, Sam, if you put 8 of them in there. The point of a decision tree is it's going to do all the work for you. You don't have to think about what variables are important. It's going to look through all of it. Does that make sense, Sam? Like, you don't have to be like, I think this variable would be good. I think this variable would be good. The tree's going to go here and just do all the work for you just like that. So the tree right here went and found that the most important variable for predicting why people think they're intelligent is because they think they're attractive. People who think they're attractive also think, yeah. It does it for you. It just picks for you. So you don't pick the variables. It picks the variables for you. So people who think they're attractive also think they're intelligent. Kind of I don't know, maybe they are. Maybe, I don't know. But people who think they're attractive think they're intelligent. There's a relationship between these variables. It's actually a correlation. Be careful with the correlation word. It's just that both of these are quantitative, so I can say correlation, even though the tree's doing a categorical break right here. There seems to be seems to be a positive association. We could look at it with a line, but we definitely see these people think they're more attractive and they think they're more intelligent. So this mean right here, this variable right here, this 63, is these 531 people but believe on average that they are more intelligent than 63% of people. I'm going to go ahead and split the tree right here. I like to do this sometimes. That's another 6% of the variation explained. And these are the people who think they're super attractive. They're just like, oh my gosh, I am the most beautiful person in the world. And they think are also really intelligent. Let's find out who thinks they're really intelligent. Let's go here. The people who think they're funny and attractive. These people think that they're super, it's so crazy. These 24 people right here, these 24 people believe that they're, on average, for these 24 people, they believe that they're more intelligent than 92.5% of people. And that's something like they're smarter, like if 10 people were around, they'd be the smartest person of the 10. If, 100 people were around, they'd be like the 92nd or the 93rd smartest person in that group. They'd be like, I'm one of the smartest people here. What does smart even mean? I don't know. But these people think, and this 92.5 is the distribution of the y variable. I think that's what a lot of people forget, is that this is the distribution of the y variable. I'm going to split over here. I just want to see one more thing. And the people who think they're the least intelligent, oh, it's so interesting. I'm going to hit Control Shift minus. There we go. Making this a little bit smaller. And this is what I would screenshot. I'd make sure you get at least this. This is not so important up here. This is going to be your tree right here. You need to have this. And I'm going to switch data sets here in a moment, so I'm not doing all with one data set. But if you look at this tree right here, the first thing I notice, and this is for a quantitative tree, which you might do a quantitative or a categorical tree, it doesn't matter which one you do. This is the distribution of the Y variable. I'm asking, why do people think they're intelligent? You notice intelligent is not in any of these. These are the X variables right here. Everything you see right here is an X variable and is a pathway people go. So you have to follow down the pathway into the least intelligent group, or the people who think they're the least intelligent, and you have to follow down the pathway. And usually it's over to the right. Usually it splits it in this way, but watch out. You want to make sure you pick the one with the highest and the lowest, or you do the group that is the most of the categorical group you're looking for. We do a categorical tree in a second. But this group has the most, it's the most like of the character of interest I want, and this is the least likely because they have the highest rated intelligence, and then this group down here is the lowest rated intelligence. This group over here thinks they're more intelligent than greater than or equal to 35%, greater than or equal to 78%, and they think they're funnier than 91%. So basically, these are my people who think they're really attractive and really funny, and they also on average think they're really smart, because that's the Y variable of interest. This group over here thinks they're attractive than less than 35% of people, and they also think they're funnier than less than 20% of people. So they don't think they're attractive, and they really don't think they're funny. And they rate their intelligence on average at 26, and this represents 54 individuals. Is this making more sense, Sam? Do we need to split our tree like that? What I would do, and this is going to be important, is we need the additional output. Let's go over here to split history, and you don't have to do this, but this seems about right to have split my tree. I don't know, it's a hard say. You need to include this graphic right here. So we need to include the split history. Split history is another graphic we need. Oh, did I lose my Word doc? Oh, no, I'm going to lose that one. We need the split history. Maybe make this a little bit smaller. I like to center my graphics. You can always do the fun things when you click on your graphics. You can always go over here and do something like that. You don't have to. That looks all right. But can we do psychological experiments sometimes involving tests the ability? Yeah, I'll do it here next, Layla. You got it. That's good. That's for today's work. Yep. So there's the split history right there. And we really see that the split history is kind of leveling off. We get a jump at the start going up from 0 to 20% to 25. It's starting to level off. Where you stop this tree is always your call. So, we don't want to, if it's leveling off, you want to stop it. But we have advanced ways of doing this in other classes. But for right now, if it's leveling off, we'll stop it. And last but not least, we need one more picture. And let's go right here. Where is it? Decision tree. I need to close this down. Here we go. Good. And let's go to leaf report. And you can also see the same sort of data you were looking at before. So can you do an example of the T? You bet. We're going to do a T, and then we will do Layla's question here. And there we go there. There's the same information from the tree. Your tree does not have to be quantitative like my tree. You'll see the distribution of the categorical variable here, or you'll see the mean of the Y variable. And you can see our most intelligent people think they're the most intelligent, or you can see up top the people who think they're the least intelligent, like they rate their own intelligence at this level. Good stuff right there. Let's do, what did we say we're going to do next? I think we're going to do a t-test next. Should we do a t-test? We'll do one more thing on the project. So there we go. A little bit of talk on decision trees. We'll do a t-test, and then we're going to do the psychological rat experiments. Let's do it. Okay, here we go, t-test. Let's do this. Okay, so we're going to pull up a different data set right now. Let's pull up the diabetes data set. So we're going to pull up different data set. Here we go. And this one, if you don't have the pregnancy test, that's all right. I made this on whether or not someone had been pregnant. So if you do want this, email me and I will email you. It's just created yeses and nos if someone has or has not been pregnant. So it's no if they've never been pregnant. And then yes, some individuals have been pregnant as many as 17 times. And let's do this right here. Yeah, two good questions right there. The 1,000-chip trial and the psychological experiments. You got it, Carly and Layla. Yep. So when we do a t-test, what kind of data are we analyzing? This kind of relates to what we're doing today right here. So when we do a t-test, what kind of data are we analyzing? When we do a t-test, what kind of data are we analyzing? And I almost said this in class, and I realized I kind of said it one time, but I didn't. I said, Mr. T is mean. If you're doing drugs, he is mean. Mr. T is mean. So what kind of data are we analyzing when we're doing a t-test? Because Mr. T is mean. if you're doing drugs. So what kind of data are we analyzing when we do a t-test? What kind of data are we analyzing when we do a t-test? When we do a t-test, what kind of data are we analyzing? What kind of data are we analyzing when we do a t-test? As Mr. T is mean, quantitative means. So quantitative data. So how about we see, let's try to see for this group of individuals, on average, how many times they were pregnant. So I'm just hopping different data sets so people can't do, like, come up, don't worry. It's not the end of the world if you do the same things I'm doing, but I like for people to do new things. But let's go ahead and look at pregnancy right here and see on average how many times people were pregnant. Let me slow this down. We're going to go here to analyze distribution. Analyze distribution is where you go when you want to analyze one variable. And so with this one variable we're going to analyze pregnancy just to see on average how often people were pregnant. And it's going to do a lot of the work for us. It is a right skewed distribution, but our sample size is 392, which is more than large enough. So because our sample size is large enough, we can do confidence intervals for the mean. And we actually see a confidence interval right here. And with this confidence interval right here, you'll notice that the confidence interval goes from 2.98 to 3.62. So while I create this next bit of test, I am blank % confident that the true blank of, well, we can just leave that. I'm going to come back to this. But I am saying right here, I am blank % confident that the true blank is contained in the interval blank to blank. Who can fill that in? Remember what I'm testing right here? I'm testing something about them. What am I testing? So try to fill in, I am 95% confident that the true what, like what am I testing for this? What am I trying to understand for this group? The blank amount of blank for the group. And let's do a last thing. This is the last part of it. Let's test the mean. And let's see if they've been pregnant. Did I say you have to do the does not equals test? Yeah, I think I did. Let's see if they've been pregnant 2 or not 2 times. And this is what we'll be doing tomorrow. And we will be getting into this, so you'll see more on this tomorrow. And that is the test right there. This p-value right there is the test. So what does this test mean? I want you to just think about this for a moment. Just look at the interval and only the interval. With only looking at the interval, would you believe 2 or reject 2? I just want you to look at the interval above my head right there. What would you do? Would you believe 2 or reject 2 as a value of truth? So look at this interval, and I want you to tell me 2, not 2.9. I want you to tell me 2. Do you believe it or reject it? Because the interval is, I am 95% confident the true mean amount of times these women have been pregnant is contained in the interval 2.98 to 3.62. So would you believe 2 or reject 2? Because you believe, you're 95% confident the truth is in the interval 2.98 to 3.61. So do you think 2 is a true value, or 2 is, no, I don't believe 2 is true. I am 95% confident the true mean amount of times these women have been pregnant is contained in the interval 2.98 to 3.62. Would you believe 2 as a value of truth or reject it? You would reject it. And why do you reject it, Sam? Something we're going to talk about in depth tomorrow. Why are you rejecting it? Just think, you're saying, I believe the truth is 2.98 to 3.61. So you're rejecting it because it's what to your interval? You are rejecting that value because that value is outside your interval. And this is the two-tailed test right here. And let's talk for a moment about how a two-tailed test works. A two-tailed test, it's outside the interval. Exactly. So if I told you the new Nintendo system is going to cost somewhere between $400 to $600. Your friend says, I heard somewhere it's going to cost $900. What would you do to that value of 900? That value of 900, you would reject that value. You'd say, that doesn't seem plausible. Brian said he's 95% confident it's going to be between $400 to $600, so I reject the value of 900. That's outside of the estimate. But if they were to revise their estimate, and they were all of a sudden have an estimate like 455, for some reason, weird sort of numbers right there, 455 is within the interval, so you would not reject that interval. This is now a value we would not reject because it's contained within the interval. And when you think about how confidence intervals work, and we'll see this tomorrow, confidence intervals look like this. A test, a two-tailed test, looks like this. So a confidence interval at 80% would come to the same conclusion. They're all fine. I mean, you can double check if you want and send it to me and be like, does this look okay? Just make sure it's quantitative for a t-test. Has to be quantitative. A confidence interval for 80% would be the same as doing a two-tailed test. So this is the does not equals test with an alpha equal to what? What do you think alpha? And alpha is percent under the curve. We usually do it as a decimal. So we don't usually do alpha as like a percent. You could say 20% alpha, but we usually do it as a decimal. So what do you think the alpha would be relative to this two-tailed test? So when you look at that confidence interval, then what would be the two-tailed alpha? Just think about how this works and what alpha and this are right here. What do you think the alpha would be right here? Which there's my Pearson questions that ask this. It's like we make an 80% confidence interval. What is this alpha level on a two-tailed test for this? So the alpha level here would be what? What would the alpha level be? Just look at it visually speaking. Yep, that's it right there, 0.20. It's just the outside, so it's 20% alpha or 0.20 alpha. It's just the inside outside. And you might have been seeing some of this output if we did things like, we'll go do this real quick. Analyze distribution. We look at the age of students. And right here, we'll just stack this. We got some points colored for some reason. And then we go here to confidence interval. And you go to 90% and take a look right here. With this 90% confidence interval, what do you see? It says 1 minus alpha. So a good note to have is that alpha and the confidence level are complements of each other. So 1 minus alpha is the confidence interval. So you're seeing right here, it's just basically saying 10% alpha is relative to a 90% confidence interval. And that's what we're seeing visually over here when we talk about alpha and confidence intervals being complements. It's just that if you add alpha, right here, alpha and the confidence interval, you will get 100%. And we're seeing that there in the output right here, that 1 minus alpha is the confidence level. They're just complements of each other. So when you look at this, if I were to test, I can tell you the p-value on this. Are you ready? I'm going to go here to, oh, it's so close to being on the screen. There we go. I'm going to go here to test mean. I'm going to test the value of, and this is how you do a test. We've done a few of these already, or we've done one of these. The p-value for the two-tailed test will be exactly 10%. Are you ready? There it is right behind my head. And the reason I know this is I chose the value on the very edge of a 90% confidence interval. So what I'm doing here visually, when you think about what I visually did, is I chose the value right here, and that created a p-value right here. So I'm able to accurately know when something would be rejected. So this is the value that would just barely not be rejected. So I tested this value that would barely not be rejected with a 90% confidence interval, and that means my p-value right here would be 10%. This is a big concept. It's something new we haven't covered. If you understand this, you understand the in-depth way of understanding it. Who understands this right now, that since this value is at the edge of a 90% confidence interval, we would not reject it just barely at the 10% level of significance on a two-tailed test. This is the two-tailed test. And so that value was at the edge of a 90% confidence interval right here. That's where the value was at. And it was just barely at the edge, or rather, this was the tested value and there was the observed value. Does anyone get that? I hope. This is something we'll be covering in depth tomorrow. We're going to do a full, 30, 40 minutes talking over this. This is more in depth tomorrow. And this is the concept today. And then we're going to talk about how it connects to testing values. Any questions on this right now? But this is all the output. So if you've made the output, interpretations will go more in depth tomorrow. So good questions right there. Good stuff. I think we had some chapter 14. We'll come back to the project here in a little bit. Let's go see those chapter 14 questions. Okay. We got the psychological rat experiments first, and then we got 1,000 chip trial. How's it going, Sam, with the project? How's the project looking, Sam? We'll see how everyone's doing on the project. I think these are Chapter 14 quiz. Confidence rolls. Here we go. We've done the hot dog one. We need to find rat experiment, right? And then I think we have 1,000 chips. Oh, found the rat experiment. I think this is the one where you have to remove the outlier. Good, I'm going to finish up the homework so I can start that soon. Awesome, great job, great job. Let's do this, let's hop into the assignment. Here we go. We need to create a 90% confidence roll, and we have jump. Yes, thank you. Okay, so you're going to see a lot of what we were doing in the assignment right here. You're going to see a lot of similar work. We're going to take the data right here and go to copy to clipboard. So with copying to clipboard, you notice there is a column name. Please notice that when you hit Command C or Control C, since there's a column name, when we go over to jump right here, we're going to go into jump and we're going to go to File, New Data Table. File, New Data Table. Under File, New Data Table, remember there was a column name. So since there was a column name, don't click inside of here. Go to Edit, Paste with column names. Very key. You must paste with column names because there was a column name. So now you notice time goes up here. If you see the following, please start over. It should not be red. It should be blue. This controls the data type. Just start over and make sure to paste with column names. So now that we have the data pasted with column names, edit, paste with column names, start over if you broke it, just start back over real quick, rewind the video. And so we have the data pasted in here. We're good to go. It's blue. Make sure it's blue. Create a 90% confidence roll. Cool. Okay, let's go here to analyze distribution. Let's zoom in on this so you can see it even better. Analyze distribution. Analyze distribution allows us to analyze univariate quantitative or univariate categorical data. And we're going to go right here and just double click. And there we go. We have the variable inside of here. And we're going to click OK. Let's click OK. So there's the shape of it. Now you notice it doesn't look quite like those shapes. Looks a little different. There's an outlier up here. So we might be able to identify this pretty quickly. These two have outliers. This one has they have a little bit different of a shape. They go from 20 to 100 in units of 5. So let's go back to it. I need to close down jump. It's getting a bit ridiculous. 20 to 100 by units of 5. So you double click on the line, type in 20 to 100 by units of 5. And then you click OK. And you see we've got that little peak right here. So this is the one. This is the one. We probably could have found it by looking at some other stuff, but that helps us find it pretty well right there. And so now we didn't write in the confidence roll. 90% confidence interval. With a 90% confidence interval, I've still got it open right there. So with the 90% confidence interval, we're going to go here and click on the red arrow right here, go to confidence interval and 90%. So click on the second red arrow, go to confidence interval and 90%. And now we get, I am 90% confident the true mean time it takes for these rats to complete the maze is contained in the interval. We have the lower and we have the upper. So we're going to keep this a little bit minimized here as we work on the problem. And let's move this over here. We can see it on the screen. There we go. So the lower is 46.45. And the upper is 56. And we're just going across here. The mean, lower, the mean, upper. Just see how they crisscross. Lower, mean, upper, mean. There's the estimate, the sample mean. 7, 8. There we go. That should be correct. This problem takes a turn, though, right here in a moment. It wants to know the goodness of fit plot, or not the goodness of fit, the normal probability plot. Now, normal probability plot always goes up and to the right, and if it follows a line, it's a good pattern. If it doesn't follow a line, it's a bad pattern. I've never seen one that looks this crazy, but something you'll notice is we have this high outlier. This gap right here in the data, this is the true one. Yours will look similar to it. This gap right here is created because in the histogram, we'll take a look at it right here. There's the actual histogram. This gap right here is the gap. These are the observed values. You notice there's a big gap in the observed values right here, and there's the big gap. None of the other ones have a really big gap. Maybe this one does, but normal probability plots generally follow a straightish line. This one just can't exist. That's not how it's made. This one Sometimes people make them in a different direction, but this one's perfect. And also it doesn't have the high value. Notice our high value here are nearly 100. The high value up here of nearly 100. These are the observed values once again. So this one would be possible, but that's not how normal probability plots look. They are slightly linear or slightly bent, and they don't just randomly jumble. It's more like a residual plot. So check the conditions right here. Ooh, hard questions. Whenever we get to the conditions stuff, this is where the tricky stuff comes out. Okay. So with the conditions, randomization is met. Sure. The normal probability plot is roughly straight. Here's the ones mentioning the outliers. So we got it right down to here. It's got to be one of these. The histogram is unimodal. Oh, it says no outliers. No other outliers. Okay. Yeah, it's unimodal. The histogram is unimodal, so it's got to be one of these two. Is it skewed? Okay, good. This one says without the outliers, the conditions seem to be met. Okay. Because we're going to go here and remove the outlier. Without the outlier, the conditions seem to be met. I love how they use like slight wording, like it seems to be met without the outlier. That's good right there. So now we need to remove that outlier, and this is where the fun begins. So you can easily remove the outlier with the following. So watch this. Do this in this order. To remove the outlier, go here to the top and go to the redo automatic recalc. This is a very important button to click. If you don't click this button, it won't redo it. So we're going to click automatic recalc, and then we're going to select the point. You can click it as long as you see this highlighted, you're good. And then go up here to rows, and under rows, we're going to go to hide and exclude. Now watch your output, because when you click this, your output will change. And it just removed the outlier. So the outlier has been removed, the output has been recalculated. Maybe that rat like is injured or something, poor rat. So we have now excluded that point from our observations. With that point excluded right here, let's go into here and let's talk about the interval. I am 90% confident the true mean time for these rats going through the maze is contained in the interval 45.63 to 53.39. There we go. We got the interval calculated right there. Does this maze meet the requirement of at least 1 minute? This is, once again, we can reject that value. We can reject the value. The maze does not meet the requirement. Both intervals are entirely below. The maze does not meet the requirement. Both intervals are entirely below. 100%. Streak continues. So we got this right here. Good stuff. Let's go do that 1,000-chip trial. 1,000-chip cookie trial coming right up. Here we go. Layla, were you able to get 100 on it? That's probably one of the toughest ones because you have to go through and remove the outlier. But I hope Layla and everyone got 100 on that. Let's go ahead here and start looking at the next one, the 1,000-chip trial. Let's do this. Okay, here we are with the 1,000-chip trial. We've got here 10 observations or 12? How many observations? 1, 2, 3, 4, 5. 10 observations. This is going to be another jump problem. Much easier to work with data in jump. We're going to copy to clipboard. And when we copy to clipboard, we're going to hit Control-C or Command-C to copy it. Now, you can go to any of your 10,000 worksheets open in jump. I'm going to go back and watch you do it again. Yeah, good job right there. Great job, Layla. You can go to File, New, Data Table. File, New Data Table. Now, this one did not have a column name, so you're just going to go to Edit, Paste. And what do I mean by column name? When you go to copy it, you'll see either a name at the top. If you see the name, paste with column names. If you don't see the column name, don't paste with column names. You don't want to see the numbers appear up here because if you paste with column names right now, you'll see the number in the first column, and that's an issue right there. So watch out. That is an issue. Okay. So now, let's go ahead and run this. Analyze distribution. With analyze distribution, we're going to double click the Y variable and click OK. And then we're going to go to the top right arrow and we're going to go to stack. And there we go. There we go. We got the data ready to go. Let's full screen and we'll come back to this here in a moment. We have analyzed the data. Check the conditions right here. The sample is less than 10% of the population. Good. No. The random is usually where we assume independence from. So the data is from a random sample, so one can assume they're independent. That's why I usually just check random. If it's random, it's independent. So did we randomly collect this data? If not, there might be issues of independence. So conduct a histogram of the data. Construct. It's going to be slightly normal. If you notice, this one starts at 900. This one starts at 700. That actually eliminates which one it is. But we can show this also if we go here. I think it was 900 to 1300. Was in units of 100. Oh my. There we go. Look at that. So we can construct the same shape that they have with theirs. Just seeing this right here, there's the shape that looked to be about the number line they created. And we can see the same exact shape. Oh, they go to 1600. Yeah. So I went to too small of a number line to start. The histogram is definitely unimodal and symmetric. So I think that's got it. The histogram is unimodal and symmetric with no outliers. You can eliminate down just right here. It's unimodal symmetric. So we're good on that. I think we've got everything so far. Yep. Now we need to create a 95% confidence interval. And I don't think I minimized it. Good. 95% confidence interval is right here. There's your 95% confidence interval. I am 95% confident the true mean chips in these bags. We're going and eating chocolate chips and counting the chocolate chips on the chocolate chip cookies. And we're seeing how many there are. And then we're counting how many on average there were in the bag. This is a lot of work right here. I think I did this one time in a class. I wonder if this person went to school with me who made this question. And so we go right here and we enter in the lower bound to 1 decimal. And then we enter in the upper bound. Oh my gosh. There we go. We're just taking the lower bound and the upper bound right here. It makes a 95% confidence interval by default. And that should do it on that. And so here's the part where I have made mistakes, but it's a little bit confusing. What it says right here is we are 95% confident the mean chips per bag is contained in the interval. So what does this say about the company's claim? On average, the average for the bags would be above 1,000. But one bag, sorry, 1 second. One bag could be below this. So because the interval does not include, because the interval is entirely above 1,000, the mean number of chips per bag is likely more than 1,000. However, the normal model predicts that a small number of individual bags would have fewer than this. So the normal model, if we looked at the normal model, you would see that it is possible, and we could talk about that real quickly here. The normal model, we would need to draw one with a standard deviation of 102 and a mean of 1243. So standard deviation of 102 and mean of, let's look at this again. So standard deviation. Oh no, did I minimize? Yes, here we go. 1243, 102. And you can see right here, the normal model predicts that there could be individual bags that have a mean below this. Not a mean, excuse me, just, here we go. And there, if we go below, yeah. So about 1% of bags would have less than 1,000 chips. But the mean, when we talk about the mean, we're 95% confident the true mean for all bags, like on average for all bags. So we're not concerned about one bag right now. We're saying on average. So our company could claim on average our bags have more than 1,000 chips, but it could be that a single bag of chocolate chip cookies don't have 1,000 chips. So hopefully that makes sense that we have good evidence that on average we have more than 1,000 chips on average, but individual bags of chocolate chip cookies could have less than 1,000 chocolate chips in them. So that's what we're talking about here when we talk about the mean versus a single bag of chocolate chip cookies. That's got it. Let me see here. Ritu had some questions. Let's hop back here. What other questions were there? I think we might hop to Ritu's questions. We'll try to do... Oh, music didn't play. What questions are there? Let me know. We'll hop to Ritu's questions, I think. What are people working on? Let me know. Let's see. If you're working on something right now, just put it in the chat. We'll take a look at Ritu's. Can we go over Canvas Content 9? I think we do some Canvas Content 9. I think that's got it. Put your questions in the chat if you have them. Let's go here to Canvas Content 9. Thank you, Ritu, so much for waiting. I always try to do the most newest. I try to do the newest or most relevant things first, and then we usually have time, which we do today, to go back and do some stuff that we'll be doing tomorrow. And it's always good to get ahead. Canvas Content 9 due Wednesday. with the mini project and all that great stuff. So let's go ahead and do a version of it right here. Canvas content number 9. Here we go. Chances flight will leave. You got it. We'll do it next. Hoping to lure more shoppers. We got 2 questions. We'll do canvas content, and then we'll come back here and do those right here. So let's do a version of the canvas content. Here we go. Okay. A new diet is being tested. The inventor claims people lose 10 pounds on average the first 6 weeks. After 6 weeks. Be the first. 25 people are randomly picked to try the diet. Researchers are convinced the inventor's claim is exaggerated. The sample yields an average of 8.5 and a standard deviation of 6. Calculate the appropriate test statistic. Wow, that's a lot of work. That's a lot of work. We'll be doing this tomorrow. It's a lot of work. Okay. So with this one right here, we're doing a test on the mean. This is a 1 sample means test. Let's highlight our numbers. 25 is the sample size. 10 is the claim. 8.5 is the sample mean. And that's the sample standard deviation. This is a new symbol. This is mu naught. That is the hypothesized mean. That's the sample mean. That's the sample standard deviation. And that's the sample size and the degrees of freedom. Who can tell me the degrees of freedom while I write out the equation? Who knows the degrees of freedom for this 1 sample t-test? So think about it. We just did something like this today, and I'm writing out the equation. So who knows the degrees of freedom for this 1 sample t-test? This is a 1 sample t-test right here. Who knows the degrees of freedom? So what would the degrees of freedom be? Which actually we don't need to solve for that, but because we're just solving the test statistic. It's not that much work. 24, great job, CAD, right there, n-1, so the degrees of freedom are 24, and that would tell us which t distribution we're using. We're actually solving for a t right now with n-1 degrees of freedom. Square root of 25. Oh, that makes life easy. So, yeah, we basically have this right here. So this is negative 1.5 over 6 and 5. And so 6 divided by 5 is that. And 1.5 negative divided by that is that. And that should be the answer. That should do it. Not that bad. Seemed like it was going to be longer than it was, but just knowing some notation, we got this. A new diet bet is being tested, which is the correct set of alternatives. Now, here's something we should always know. I want one person to write this in the chat because this will eliminate us down to 2 answers. The null has the equal sign. The null has the equal sign, and we'll see this. We'll be repeating this. This question right here, you can eliminate it down to 2 answers just by knowing the null has the equal sign. We will say that all throughout the week. Whenever we write nulls and alternatives out in statistical notation, we'll just say the null has the equal sign. And I'm talking about this right here. The null hypothesis has the equal sign. So you're literally down to 2 answers just by knowing the null has the equal sign. Then the only thing we change, and we'll see this a lot tomorrow, is we will change the sign for the alternative. So they're saying that they will lose 10 pounds. So they would want them to show that they lose more than that. That's the claim they're showing. So the null is that you lose 10 pounds. The claim they're trying to show is that you lose more than 10 pounds. I know it sounds crazy to say, well, aren't they trying to say you lose 10 pounds? Well, we're trying to show evidence you lose more than 10 pounds. Like you will lose at least 10 pounds. So that is the claim being tested right there. Do you lose at least 10 pounds with this diet? So they're trying to show evidence of that right there. If we construct a 95% confidence interval that does not contain the hypothesized value, which of the statements is true, this goes back to something we were talking about earlier, where we can reject values that are outside the interval, If a value is outside the interval, like 1,000, we could reject that. But if a value is inside the interval, like 450, we cannot reject it. And this goes to what's going on here, that values inside the interval can be rejected and values outside the interval cannot be rejected. So if a value does not contain, the value can be rejected. So we can reject the value at the 0.05 alpha. And we also mentioned how the confidence interval and the alpha are complements of each other. So check out that part of the video earlier where we were talking about the confidence interval and the alpha are complements of each other. So a 95% confidence interval would be the same as doing a 2-tailed test with 0.05 alpha. So we have that right there. A smaller p-value provides stronger evidence against the null hypothesis. No text provided. That's the best answer right there. That needs to go in and be fixed. So they'd better not have done. We usually think of I'm gonna be really mad if I'm like, who wrote this question? Because I would phrase it, because you can always like debate things. If you ever see a question you think that is wrong and you put something, please tell me. Because what I would say is a smaller p-value provides stronger evidence for the alternative, but it is against the null. It's good reason to reject the null. So I'm going to say true right here. Because a lower p-value, a smaller p-value is more evidence against the null. That makes sense. It's more evidence for the alternative, which is against the null. When we reject the null and the null is true, type 1 error. We will do this a lot. In a type 1, the null is true and we reject it. There's the T. In a type 2, the null is false and we fail to reject it. Whenever people miss this question, it just hurts. There's a report I can get on the test that shows me which questions people are getting correct and which questions people are getting wrong and how it relates to those who are understanding the test versus not understanding. And this was one of the top questions. This question right here is one of the top questions that people who know the material get right and people who don't know the material get wrong. So this question separates out the people who know what's going on versus the people who are just guessing. Like this is considered one of the best questions. And it's just knowing that in a type 1, the null is true and we reject it. There's the T. In a type 2, the null is false. That's an F and we fail to reject it. So that would do that right there. We should get 100 unless they tried to trick me with that 1. Oh, ooh, wait, what? Wait. The null is that less? Wait, what? The inventor claims are the... Researchers are concerned that the claims are exaggerated. I am really unhappy with that question. I'm going to actually talk to Charlie, Missy, and everyone. Not Missy anyway. But because they could test both ways. I really don't like that question. Please tell me if you got that one wrong. Because they're trying to show... So the correct answer, apparently, is going to be the less than. Because they're trying to show they're exaggerated. They're trying to show researchers conduct... I'm going to go and look at that one. I don't like the way it's flared. It should say researchers want to show evidence the claims are exaggerated. So I might even change that. Let me go change that one as we speak. 2 seconds here. Let's put on the music. I'm going to change the way that one's worded. Because we talk about showing evidence. If it's not clear, don't like the way that one's worded. Let's see, we're going to do some more. That is, the streak is over, everybody. That's it. We went Monday or Tuesday to Monday. And that's the end of the streak. We got to start a new streak now. A new one. Let's go to manage. We're going to change that one. Chapter 15. It's going to have different phrasing. Here we go. Found it. So researchers are concerned this claim exaggerated. They wish to show evidence people are not losing as much. Not losing. They wish to show evidence people are not losing 10 pounds on average. There we go. Question makes a lot more sense now. Cool. Should be updated. Let me go make sure the Canvas content, because I updated the question bank, so it should do it now. And that should be saved. Okay. Question is fixed. We're good to go. Let's see right here. Hoping to lure more shoppers downtown. Let's go take a look at that one right here. Hoping to lure more shoppers downtown. Here we go. Let's do it. Hoping to lure more shoppers downtown as city builds a new public parking garage in the central business district. The city plans to pay for the structure through parking fees for a random sample of 42 days. That sounds like sample size to me. Daily fees collected averaged $131 with a standard deviation of 16. Complete parts A through E. So we have here, did they sample at least? No. We don't want to sample at least. We don't want the samples to be dependent either. They should be independent and they should be less than. So what assumptions must you make? We want them to be a random sample of days, and we want the data to be basically unimodal symmetric with no outliers. The more normal it is, the better. To create, hey, what's up, Joshua? Cracking me up right there. Yep, short hair Brian again. Today's the day, the first day of short hair. Good to see you here, Joshua. Good to see you swing by here. So we're going to make a 95% confidence roll. Let's go grab that T statistic. So we're going to go get the T statistic for a 95% confidence roll. And Layla, do you know the T statistic? This was Layla's problem right here. Layla, do you know the T statistic for this? I'll start marking the notation. Mubot's going to help us find that T statistic. We need to know here the sample size. There's the sample mean. There's the sample standard deviation. We need the formula. The formula is y bar plus or minus t with n minus 1 degrees of freedom, star for the percent we're choosing, s over square root of n. Degrees of freedom are 41. df equals 41. This is n right here, and is sample size. Y bar is this, and s is this. So go ahead and find that t real quick, and then I'll find the t. See if you can find the t. And so yes is 16, square root 131, and then the y bar is 42, 131 plus or minus. Now we need the t. So we're going to go over here to the t applet, and we're going to put in the 41 degrees of freedom and 95% confidence, which is actually already showing 95% confidence, and we had 2.02. So once again, put in your confidence. You might have, maybe you have 99% confidence. If you have 99, it would be that. If you have 95 like me, it would be this. So if it's 99, then that is correct. Mine's 95, right? So mine's 2.02. Mine's 95. If yours is 99, that is correct. If yours is 99, that is correct. So just make sure you have the correct one for your interval. So great job. I think you have 99, right? Or you have 95 and you didn't change it from a previous problem. So I have 2.02. Yours is wider because it's a 99, which goes to the idea of if you have a higher percent confident, you're going to have a wider interval. So we got it. We're good to go on this. We just need to solve 42 square root 16 divided by times 2.02. And there we go. It's basically 5. Oh, it's so close to 5. So close, but not. And so this will be 131 plus this. Oh my gosh. There we go. $987. There we go. 126.03. There we go. I think that's got it for that. Well, let's go ahead and take those numbers and plug them into here. So the confidence interval goes down to 126.01, and then it was 131, right? So that's 135.99. Should be correct. Hopefully we carried all our decimals. Explain what this means in context. I am 95% confident that the true mean for the daily income will fall or is contained in the interval. That the mean daily income will fall in the interval. We're 95% confident. There's 95% confident. I think that's one. Man, they love putting things so close. There is 95% confidence the interval contains the mean daily income. There's 95% confident the mean daily income will always fall. Okay, that always word's a giveaway that's not the right answer. Will always fall. We're 95% confident that the interval contains the mean daily income. This always is the throw-off word right there. I was like, they're similar, but then once they say always, I'm like, don't say always in statistics. Explain 95% confident what it means. 95% of the time, 95% of random samples of this size will produce intervals that contain the truth. So we're talking about in the long run right here. We have a slide going over this. So in the long run, 95% of 95% confidence intervals are expected to contain the truth. And that's what 95% confidence means. It's not about one interval containing the truth. It's about if we repeatedly create intervals. In the long run, creating intervals, here's the truth right here. This green line's the truth. And we see some intervals do not contain the truth, and some intervals do contain the truth. This is the interval right here going to the upper and the lower. So 95% of 95% confidence intervals are expected to contain the truth. And that's what we're saying right here is that 95% of random samples will produce confidence intervals that contain the truth. So they're creating confidence intervals, and 95% of the time they'll contain the truth. What we're testing is 129, and is 129 in the interval? 129 is in the interval. So since 129 is contained in the interval, the consultant's prediction is plausible. Let's go for that 100. Boom, we got that 100. You know what's happening right here. One mistake today, that's fine. Not today, my Pearson. I think we have one more question at least. Let's see right here, the chances of a flight leaving on time. Let's do CAD's question next. Okay, let's do CAD's question right here. We've got the chances of a flight leaving on time. And let's find it. A little music right here in between segments. I'll go to this one. Chances of a flight leaving on time. Is this, will your flight get to your destination on time? Is that it, CAD? One of them says, will your flight get, here it is. We got it, I found it. Let's do this. What are the chances your flight will leave on time? To the right of the histogram and the summary statistics for the percentages of flight leaving on time, 2001 through 2006. There's no evidence of a trend over time. They're getting into some time series right there. Complete parts A through C. Check the assumptions for the conditions. Are these independent? Maybe. Probably. Is the randomization met? Sure. Yeah, maybe. Are these less than 10% of all flights? It's a random sample of 72 flights. Sure. That's less than 10% of all flights. Is that nearly normal? Yeah, that's nearly normal. For once, I'm very happy. I mean, 10% I'm happy about. But this is pretty unimodal symmetric. Not too much of an outlier condition going on here, but mostly unimodal, mostly symmetric. Looking pretty good. You can examine the histogram to look to see if the nearly normal condition is met. So we're looking pretty good right there. That one I like. That one I'm very happy about. Create a 90% confidence roll. This is where we need to take the data and make the 90% confidence interval. Okay? So let's go ahead and remember our equations, which are going to be key. See the equation right there, but let's rewrite it. So we will give you the T on the test, but we're only missing one thing right here. So CAD, Layla, anybody, help me. We're missing one thing, which is going to be very important for creating a 95% confidence interval, which we'd give you on the test. I'm saying down here, maybe. What are we missing right now that we need to get that T? They didn't give us this value, and this is a one sample T. That's the best way to remember what the degrees of freedom are for this. So what do I need right here? I need the degrees of freedom, and what are the degrees of freedom? Because they didn't tell me them. They did not tell me the degrees of freedom. Degrees of freedom 71. Great job, CAD, right there. There's the degrees of freedom for a one sample T. We will use different degrees of freedom for different tests. Great job, Layla. Let's throw some 50 points out here. So we have the one sample T has 71 degrees of freedom and -1, exactly. One sample T and -1, one sample T interval, one sample T test. So now we go to our T applet, which is on the screen. And here's the T applet, 71 degrees of freedom, 90% confidence. And the T statistic is right behind me right here, 1.667. And we just go back here and we plug in the T. So the T is 1.6. Oh my gosh, can't see that. 1.667 because it's 90% confidence for a T of 71 degrees of freedom. The S right here is going to be 2.69753 and square root of 72 plus or minus. So there, yeah, great job, Layla. Yep. I think you got it. What do you think about this chapter now, Layla? Like, hopefully it's feeling a lot easier. If you just started it this morning, great job, because you're acing it right now. Like, you're doing great. This is what I love to see. I love to see people who are just, you practice it and then you're like, okay, I'm getting it down. It's just practice. A study measure the waist size of 999 men, chapter 14. We did that one during class day. We can do it here at the end because I don't know if there's any more questions. We did that one at the very end of class today, unless there might be two like that. Maybe there's a second one just like it. I'm trying to think if there's another one that does waist size question. We can do it again though. We can do it again. I always try to do the repeat ones toward the end. I can't write. Is that it, Layla? Oh, Layla, thank you so much. That does look to be correct. Layla just solved out the math right there. I'm going to trust Layla on this one. So Layla says 79 point. That does look to be correct. That's so awesome, Layla. Great job. That's what I like to see is like by the end of the day or by the end of class, by the end of office hours, you're like, I got this. And that way you can kind of have the rest of the day off. And there was two of the waist one. Oh, then let's do the other waist one. Sorry, Carly, right there. Let's do it. I was like, are there two of those? And so there are. Let's find that other one right here. Thank you, Carly, so much. Let's throw some 50 points. Thank you, Carly, so much. I always like doing as many questions as I can because I know people come back to watch the videos. So my goal is like, let's do as many as we can. So we have this right here. Let's go here. Let's make the interval 79.93, 80.99. We can be 90% confident the interval contains the true mean. So just when you get the wording down, these are a lot easier. I am blank percent confident that the true blank is contained in the interval blank to blank. 100, yeah, we got this. Yeah, let's go take a look at the chapter 14 sampling distribution 1. So here we go. Let's go ahead and take a look. Chapter 14 sampling distribution. Chapter 14. Chapter 14 sampling distribution. Okay, waist size. Here we go. We got it. You are 100% correct. Thank you so much, Carly. This is a new question we have not done, so let's go do it. Study measured the waist size of 982 men, finding a mean of 36.27 and standard deviation of 3.96. A histogram of these measurements is shown to the right. A little bit of right skew right here. Describe the histogram of the sizes. Well, did I say right skew by accident? I meant to say left skew if I did. Left to the low, right to the high, whatever way the tail goes. So we're going to look at the central limit theorem right here. What you'll notice about the central limit theorem is that the distribution becomes more and more normal as the sample size increases, and also the standard deviation gets smaller. It might be hard to see that the standard deviation gets smaller, but it does, and reason being, let's see if I can increase that window size, but I can't. The number line gets smaller. The number line, which usually you can see right here. Really? The number line on this one goes from 33-ish? I don't like the way they done that. 33 to 39-ish. And then down here on the very first one, it's all the way down here at 28. Much longer number line. So it's becoming tighter and more normal. And when is it normal? Either 5 or 10. Ooh, did they finally say that? Oh, I think they changed around their question because they used to trick me on this one. These simulations do demonstrate what the central limit theorem says about the sampling distribution for the sample mean. It's becoming more normal and tighter. You notice right here, it's skewed to the left. And as we increase, you're seeing at a sample size of 2, more normal, tighter, more normal, tighter, more normal, tighter. Ah, you bet, CAD. We can definitely do that one. So the histograms, and this is the center. So as n gets larger, the histograms approach the normal shape. If you notice right here, this is approaching the normal shape. More normal, more normal, more normal as n gets larger. And the variability in the sample means gets smaller. The histograms are fairly normal by the time they reach sample size 5. I think this used to be a blank people had to fill in, and maybe they noticed that people just... It's hard to tell. When is it normal? Is it normal at 5? Or is it normal at 10? Or is it normal at 20? That's the judgment call one. And statisticians would be like, it just gets more normal. And that's what's true, is that it's always getting more normal as n is increasing. When is it approximately normal? So fairly normal, approximately normal. Good stuff right there. Which of these are true about the t distribution? That's a fun right there. We'll put a... Wait, is it? Should be right here. Let's go do that, which is true about the t distribution. Here we go. I'm back. Let's go get the which is true about the t. I think that's chapter 14 quiz. Or the second part of 14. So... which of these is true about the t? Aha. Okay. I need some big help here on this one. Let's help out. Let's do this. Which of these is true about the t? So what do you think? Appear demonstrates something from... I think is that the answer right there? So... what is true? If we increase the degrees of freedom, will the t become more normal? If I go right here to a t, and I increase the degrees of freedom, will the t become more normal? Yes or no in the chat. If I increase the degrees of freedom, will the t become more normal? Is that true? Are you noticing as I increase the degrees of freedom, does the t go towards the normal? And they might be Layla. If I increase the degrees of freedom, does the t start to become more like the normal? Does Mr. T say, okay, you can be more normal right here? That is very true. So that's a true statement. T distributions have fatter tails and narrower centers. Let's take a look. If we look at a T, does this look like the tails are fatter? I'd say yes. Does it look like when you go back to a T right here, does it have a narrower center? It does. And the narrower center part might be hard to see, but it's just more narrow in the center. He smashes it down. But the fatter tails is the easier part to notice. Like if you make it more like the normal, you can see the tails are flatter. We're talking about this area right here, and then you can make the tails fatter by doing this. There's more area. That's what fatter tails mean, just more area under the tails. And you can see with more degrees of freedom, you start to see less area under the tails because it starts to look more normal. So the T does have fatter tails. It just might be hard to see at higher degrees of freedom because it's more normal looking then and looks less like a T. The T is unimodal and symmetric. Well, just looking at it right here, you can tell this is unimodal, this is symmetric, no matter the degrees of freedom. So that's got it right there. All these are true. The question we just did on sampling distribution I have a graph that is skewed to the right, would part B be different? It shouldn't be. Tell me if for some reason you miss a part, I'll probably give it back. And I think, did you have another one, Layla? Tell me if you miss a part and I'll give it back probably. If for some reason there was just something confusing. I think Layla was answering, appear to demonstrate the central limit theorem, histograms approach normal mean decreases fairly normal. Oh, the answer's right there. Great work. What other questions are there? Let me see if I'm going to switch back to here. But good review. Oh, this is the easiest question in the world. You guys ready for this? A, B, C, D. A, B, C, D. What is the answer? Suppose we were making a 95% confidence interval for the population mean, and we have a sample size of 15. What should the degrees of freedom be? And this is a one sample T. That's what interval for the mean means. We're making a confidence interval for the mean. That's a one sample T. And the answer is A, because it's n minus 1. And we got it. Look at that. Just n minus 1, sample size minus 1. Nice and easy right there. Thank you, Layla. So much thank you. I really mean this. Lucy came by at the start of the semester and she was saying, like help each other out, keep up the good work. I like Layla and everyone else. Layla, you've been such a huge help and I appreciate that. Keep up the work you're doing. Do this in other classes. It's much appreciated. I think a lot of people you're helping a lot of people do a lot better. And that's so much appreciated. Like, I want everyone to follow your lead. So keep doing what you're doing. You're a great example for us all. And I really appreciate that. So let's see right here. What other do we've got time for like one more. If you have another question you're working on right now, you're wondering about, we should do at least one more. I might pick it. Oh, we should. Oh, that's a super hard one. You're welcome. You're welcome. I really appreciate it. It's the more people talk, the more they interact, the more it's just like awesome. That's what we try to do. Wasn't there? I thought there was one. Maybe it was for the other quiz. We've done a lot of we've done some jump ones today. We've done some by hand ones today. So we've done a lot of really good work today on the problems. So we'll see if people have more questions. Let me go to the sampling distribution because I saw one on sampling distributions I thought we could do. That was pretty easy. Like, it's easier to explain. When I say something's easy, as long as it doesn't have too many steps, it's maybe an easier concept. Yeah, this one right here. This one right here, multiple choice. Let's go ahead and take a look. Do something from the first chapter. Yeah, CAD right here. You got it. Here we go, CAD. This is from the first chapter 14 quiz. Let's go do it. Okay. So what's the sampling distribution model? What's the sampling distribution model for the sample mean? Describe the shape, center, and spread. Choose the correct answer below. And I love that MuBot will always give us the t-distribution. So when we talk about the sampling distribution model for the sample mean, it'll be normally distributed with a center at mu and a standard deviation of sigma over square root of n. So this is just saying that the shape is normal and the center is the mean because that's mu. Let's write these out right here. So these formulas, which we've seen a few times today, we should have them. There we go. We're talking about these right here. And they are the following formulas. These formulas are as follows: mu y bar equals mu, and standard deviation of y bar equals sigma over square root of n. And if we meet all the conditions, we get a normal shape. So that's got it right there. That center is mu, and the standard deviation is sigma over square root of n, and the shape is normally distributed if we meet all the conditions, and that's the point of meeting the conditions. If a sample size is chosen that is larger, what's the effect on the sampling distribution? The center will do what? What will the center of this distribution do if the sample size gets larger? So let's just look at this right here, which is mu. What will the center of this distribution do if sample size gets larger? If we increase n, what will the center do? So there's other questions to handle this too, but what will the center of this distribution do if n gets larger? For larger and larger n, the center of it will do what? And you just look at the equation and then think just how it works. What will that do to the center if n gets larger? Hint, it's not in the equation. So what will the center of the distribution do as n gets larger? As n gets larger, the center of the distribution will do what? The center of the distribution will stay exactly the same because it's not controlled anywhere. What will get smaller? What will get smaller as n gets larger. So if we increase n larger and larger, and we'll see it right here, I'll show it in the applet again. If n gets larger, then what will get smaller? We'll go here and do this so we can see so here's an n of 2. Here's an n of 5. Here's an n of 25. The center is not moving. So the center stays the same, but what gets smaller as n increases? As n increases more and more and more, what changes? As n increases more and more and more, what changes? As n increases more and more and more, what changes? The standard deviation. Yep, the variation in it. So the center will stay the same. So the standard deviation will get smaller, but the center will remain the same. There we go. So the standard deviation gets smaller, and we can see that here in the equations, that the standard deviation gets smaller, the mean stays the same. So the mean's not going to move, but the variation around it's going to get smaller. And the variation is controlled by this right here. So the variation around it is going to get smaller. I think that's got it. Really great office hours today, everybody. Great work. Let's hop here to space. I think that's got it. Any last questions? I'm going to answer some emails, some Discord, take a break for a little bit, eat some lunch. Medical researcher has the pulse rates. Let's do it. Let's end with that question right here. You got it right there, CAD. Thank you so much. Let's do the medical researcher pulse rates. Where is it? I think that's chapter 14. Oh, Carly asked it, right? Carly asked it. My eyes sometimes see a name and I just put it together randomly in my head. A medical researcher measured the pulse rates. Let's go do that question. We got this. And you're welcome, Kat. I think Kat was saying thank you. A medical research. Here we go. We got this. You ready? We got this. Let's do this. Let's knock this one out of the park. Here we go. Are you ready? I bet we can get this one done. We got this. So, never mind. I love it right there. So when we do this confidence interval, we have right here, how do we start out our confidence interval interpretations? I am. What looks most similar to the I am blank % confident that the true blank is contained in the interval blank to blank? Which of these looks most similar to Brian's saying of I am blank % confident that the true blank is contained in the interval blank to blank? So which of these? D. Because I could say I am 95% confident that the true mean heart rate is contained in the interval blank to blank. You just notice how they have it a little bit out of order. It's just because they don't want you to be a robot, so they mix it up right here and do different ways of interpreting. So I am 95% confident that the true mean heart rate is contained in the interval blank to blank. Same thing I say, just in a little bit different of an order, and they just want to see if you can see it out of order. What's the margin of error for interval? So the margin of error is just what the length of the interval. Just type a 4-letter word to remind us. When Brian goes here and he finds the length of the interval by just taking the upper, so I'm just finding how far these numbers are apart. So we're just saying this number minus this number is the distance between the two of them. That's all I'm taking is their distance. Like, how far are these numbers apart? Like 4.4 something. Do you see it's just the distance? And then I'm going to take what of this distance? Because I got an interval, and I'm going to take half of it. CAD right there. Great job. We're taking half the length of the interval. Does that make sense? We're just taking half the length of that interval. So that's what the margin of error of an interval is. It's half the length of an interval. Here's your interval. Just your center is my face. And then you got the plus or minus. And you're taking half the length of the interval. We go here, round to 1 decimal. Sure. Bye-bye decimals. If the researcher had created a 99% confidence interval, how would this be different from a 95? Here's a 95, or rather, I can show you. Here is let's just put in some there. Here is do I have that today, really? Here's a 95. And here's a 99. So can anyone tell me the difference between a 95 and a 99? 95, 99, 95, 99. What is the difference between a 95 and 99? The interval for a 99, because the t-square gets bigger, the interval for a 99% confidence interval would be what? The margin of error would be what if we go from 95 to 99% confident. So we're more confident. Our interval will be less precise but more confident, hints for the test. So if we were less precise but more confident, the interval would be water because we're less precise and we're more confident. So the interval will be water. It'll be larger. It'll be larger. Here, I'll show you again, CAD. Don't worry, CAD. Let's throw some 50 points. CAD, thank you so much. Don't worry if you get them wrong, CAD, because this is the time to practice right here. Some 50 points, CAD, right there. Thank you for jumping out there on that limb and being like, I'm going to take a shot at this. Going from 95, no, you're fine, you're fine, you're fine. Going from 95 to 99 is going to be bigger. Does that make sense? When you see here the 95 visually, and then you go to the 99, there's more area covered because you're going from 95 to 99. So that's more confident, but the interval is less precise. So the margin of error is going to get bigger. So when you're less precise, there's a bigger margin of error. Exactly. CAD right there, another 50 points. You know what? We're putting that in MuBot. MuBot is going to get that as a quote right now. Let's go here to quotes. MuBot's getting that quote in here. That is quote 83 right there, CAD. So you can quote that anytime you want. That's one of my favorite things to say right there. Watch me. I get things wrong every once in a while. It's all right. Yep. And then once you see, you're like, okay, 95, 99. Just always be doing that. Just be like 95, 99, larger margin of error, less precise, more confident, because 99% confident is more confident. Great job, everyone, right there. Let's end here with our classic music. Let's do this. Great work right there, CAD. Thank you so much, Carly, for asking that last question. Carly, was that question right there that got us to review some important stuff to make sure we have it down. So Carly, thank you so much. Thank you, Layla. Thank you, everyone. And if you're watching this later, thank you for watching it later. I know people have lives, work, children, jobs, just everything, you name it. So much going on in the world. So thank you. You're welcome, Carly. So I understand people have to watch this later. Like, not everyone can stay after and do office hours, but great job in office hours today. We'll be back tomorrow. Email me those questions. Take a break for a little bit. Start answering some Discord and email. I'll see everyone later. You know what we need to do? We haven't done this in a while. Time to do it right here real quick. You ready? Stay tuned for a special outro. Jason, can we keep filming? Jason, let's do this. Here we go. I think this is the right one, right? Jason, we just need to film for another 4 or 5 hours. We've almost got these new intros ready. We're almost there.
This has been going for like 20 hours. This ends now.